Okay, so you're putting that circuit in those hardware.
Yeah, that's pretty much
Right?
it. Yeah.
This and the microcontrollers already have a preset of hardware in there where you just program set of rules you can set to do something.
Yeah, you can run assembly on a microcontroller. That's what you run, right? You run code, you run software. FPGAs, you make hardware. And the way Dr. Harris will talk about this, I think, like, at the end of the semester, like close to the end, she'll talk about a little bit about how FPGAs actually work. And basically what she's going to tell you is you have these lookup tables, these little memory units. So you know how when we want to derive combinational logic, we write out a truth table?
Yeah.
Well, those lookup tables are like mini truth tables. You feed them 4 inputs. It figures out which spot in memory corresponds to those 4 inputs, and then it outputs to that spot in memory. So instead of having a bunch of and ors, you have this one lookup table that takes ands and ors and takes the place of that, and it's combinational logic. And then you have registers as well, and you can interconnect them. But that's generally how you configure an FPGA. I have not looked at the homework. Great question. How many questions are there?
Oh, this one is only 3. I just mean in general because
Hopefully not longer than 5 hours. If it's longer than 5 hours, then
okay.
That's not good.
No. That is very nice to hear because these on average are taking me like 4 hours, and that's like including reading and watching videos and going to
Yeah,
sessions
that's
or
pretty
seeing
reasonable.
doctors.
Yeah.
Okay, I've been putting like not including the office hours time. I think I should
Put
be
all the
updating
time that you are actually working on the problems, all of it, because Dr. Harris wants to know.
I'm worse. I take way longer.
Yeah, just be honest.
I
Yeah.
take forever.
No, that's fine. You're learning. That's the
And
point.
I feel like I'm slow. And like I went and saw Dr. Harris for office hours, and now I'm seeing you. And like this is my final homework, but I did a whole other final homework before I went and saw her and realized I'd done everything wrong. And I'm at like 4 something hours in.
Yep.
I'm like it's three problems. And now that I like talked to her, like it actually didn't take me very long to do this version.
Yeah.
But I'm like, do I put that amount? Because that was like maybe an hour, but in
All the
reality,
time you
it's
spent
like,
working on it.
All right,
Yeah,
4
every-
hours. We're gonna say 4. All right,
Computer's
that
not
makes me
working
feel
with me.
better, 'cause I feel like other people were like, either take like an hour and they're just like looking through all this stuff.
Okay, some do. That's definitely not me.
I mean, it depends. You know, if you've already taken the class, this is your second time taking it, you're probably going to remember most of it, zip through it. Other people take, 10 hours or whatever. It's fine.
Yeah, that's me too.
Especially the first homework. It was simple stuff, but like I still had to refresh myself in a lot of it.
And then you'll see some people who spend 9 of those 10 hours working on the schematic, just making sure the lines are perfectly straight.
Oh, that's me. Look.
Yeah.
This is nice.
Yep, I would do that too. I literally had grid paper for it. And I was like,
Yeah.
Yep.
It drives me nuts if it's not like with a straight.
all right. I'm going to turn my volume up. Could you go ahead and talk in the chat just so I can see if I can hear you?
Hello.
Awesome, cool, I can. Can you hear me? I assume so.
Yes, I can.
Okay,
Yeah.
cool. I have OBS recording. And it is recording. Going for 3 minutes. Okay, cool. So what homework are we on now? I've lost track. 6. Okay, and you guys are going over timing stuff, right? Okay. What are your guys' questions?
My question on the first one, I believe, it was okay. There's like 4 registers in there.
Yeah, it's this one.
Yeah, so there's 4 registers in there.
Oh, right, it's the XOR one?
Yeah, and each register I was assuming that had its own like delay on it. And so what I did, I multiplied just the delay on each single one.
Times 4.
Times 4, and I don't think that was correct.
Okay, yeah, so let's talk about it.
Delay on the register? I thought it was on the.
Yeah, so there's delays on
Right.
the.
You have a
actual-
delay when you read out of the register. That's called, do you remember what that's called?
Yes. That is the time clock to Q.
Yeah, so propagation clock to Q or contamination clock. Yeah, TCQ. And then you have PD, that's the, or TD, that's the delay through the combination logic. And then the time you have to hold at the front of the register. You remember what that's called?
That's the T
I said hold. I shouldn't have
Yeah,
used the word
hold.
hold. It's setup. Sorry.
T setup.
So T, that's the time before the clock hits. Hold is the time you have to hold it after. I shouldn't have said hold, but anyways, those are the 3 times you consider when you're calculating the clock time. So you have the time to read out, the time to go through the logic, and then the time you have to be waiting at the front of the register. Those are the 3 terms. So it's TCQ, propagation, the clock to Q, PD, or D, the delay through the combinational logic, and then you have T setup, the time you have to be set up before the clock hits.
But then wouldn't we only have one clock to Q because we're going down the clock?
We're considering one path, that's right.
One path.
So we pick one register and say, well, which path? Is it the path from this register to here, this one, or that one? And we consider the delay of that one path, not all in sequence. So which one, if you had to guess, do you think would have the most delay associated with it? Just as a guess.
The register?
Yeah,
Or
like
the
path A, B, C, or D. Which one?
A.
A or B. Both of these are identical, right? So, and why do you say that? Just as a question.
Well, there's more gates on there associated with it, so typically there's a lot more delay.
Exactly. You have more gates that you're actually traveling through, so you're just going to have more delay for sure. Which one do you think is your slowest path? Or, sorry, your quickest path? The one that goes through the fastest?
The least gates, or here's whatever causes these delay, that would be D.
D. Yeah, and that gets more complicated, right? If you have different types of gates with different timings on them and more logic.
And
But in
that
this
was
one,
called skew, right? I guess.
not quite. So skew is when you have a time delay between, well, this is a clock skew. Clock skew is when you have a time delay between when this clock arrives and when that clock arrives. So let's say my clock source is over here by my finger. I have to run a wire from here to this register for this guy to receive the clock, right?
Yeah.
And I have to run another wire from my finger to this register. Are the lengths of those wires necessarily going to be the same length? No. So if it's a longer wire, it's going to take longer for the signal to propagate through it, right? It's not instantaneous. And so then this clock arrives sooner than that one. That is called clock skew. That's not the only source of clock skew necessarily, but that's an easy example for seeing how it can come about. Different lengths from the source.
Gotcha.
Okay, so now talking about that, I believe for that problem they just wanted you to answer the first part per day,
Yeah,
right?
no skew.
No skew stuff, yeah. We don't have to mess with it. You will have to mess with it eventually, but right now, no skew. So what does the question ask you to find?
It asks us to find if there's no clock skew, what is the maximum operating frequency of the current? So we need to find if the hold time is met to make sure it's stable, and then the frequency, which is 1 over the TC.
Yes. So we have, I'll draw my circle. Okay, cool. So I've drawn my very poorly drawn registers here as little rectangles. And we want to analyze the circuit. Now, what do they tell us about the delays of reading out of a register, reading into a register, whole time? What are all those delays that we got?
Okay. You want me to just read them off?
Yeah, just go for it.
Okay. T setup, 60 picoseconds.
Okay.
T hold, 20.
20.
TPCQ, 70. TCCQ, 50.
Here's what I'll do. So from clock to Q, it's going to be 50 to 7.
50 to 70, yeah. And then the logic delays are per gate, and it's 100 picoseconds per gate for TPD,
Okay.
and then QCD is 55 per gate.
Okay. I think that's it, right?
Yeah.
Setup, hold. Okay, cool. So we'll start with, which equation should we start with? The hold time constraint or the setup? And why?
So I always start with hold time because if that doesn't work, then you're done.
Exactly. Now, on the test or on the exam, it is going to work because she wants you to show your calculator. However, theoretically, if you were actually doing this on a circuit, you want to check, hey, does my hold time constraint work? Because if it fails, then that means there's no need to check the actual clock time you can run it at, because you can't run it at any reliable frequency. So that's very important. So typically, do the hold time constraint first. And what's that equation? Do you remember? Without looking at your notes.
TCQ plus TCD, because it's the minimum. I'm trying to find like the lowest. Fastest, yeah.
And then, how's this inequality go?
T hold has to be less than.
I'll put this equal sign here just because typically that's how it's written, but generally you'd want it like that instead to have some sort of equal one. Okay, so what is the contamination clock to Q time? What's TCCQ? What are you guys thinking? What do we got for TCCQ? According to my list of numbers here. So this one, that's contamination clock to Q. So that's the shortest clock to Q time, right? So the way I've listed it here, these are the clock to Q times. Which of these is the shortest? So that would be
And then that's on our right side of our clock, right? Like on.
yeah, that's the time it takes to get read from the clock striking here to be read out of this wire.
Yeah, the little piece
Yeah.
before the CL.
Yep. Okay, and then what's TCD? How do we find that?
Just that delay from the gates, right?
So I'll ask, what's our critical path? In this case, is it the longest or the shortest? For TCD.
Shortest.
What do you think? Longest or shortest? It is the shortest. Contamination, that's going to be your shortest, so the quickest time. So which is our quickest path? D. Yeah. And what's the delay? Through the logic. How many gates do we go through?
1.
Yeah, just one gate. That's right. So what's our delay for one gate? 55, because we're considering the shortest time possible. Okay, so our hold time has to be less than 105. Well, is the hold time less than 105? Absolutely it is, 100%. T hold is 20. 20 is indeed less than 105. So that means our hold time constraint has been satisfied. And we can move on to the calculations for the cycle time. If this was false, if, for example, this was 105 and that was 20, then that means it would be false. Our equation would not hold. And our final answer to the question would be, does not operate reliably at any frequency. Okay, any questions on this process? All right. So next, I'm going to talk about the TC. So that's the total clock time. And TC is going to be related to what? What are my terms going to be over here? Where are my sources of delay as I travel through the circuit? So we have T setup, that's over here. Yep.
T sub PD.
Yeah, TPCQ. So specifically, you said CQ, that's clock to Q, but we're considering the propagation clock to Q. So TPCQ, that's the time to be read out of this register, the longest time. And then you also mentioned T setup. And then on Discord, which one did you say? I don't know if I got the one you said.
Oh, T sub PD, propagation delay.
Yeah, exactly. Oh man, why didn't you guys tell me I was writing it down? And what's going to be the direction of my inequality here? Which one's bigger?
seconds.
Yeah. We have to make sure our clock time is at least, at minimum, it has to be this, but preferably a little bit more than whatever that minimum delay is.
Quick question.
Yep.
Sorry. But T sub hold, is it supposed to be less than or equal to, or should it just be less
that's
than?
right. So
Less than,
the
right.
way that T hold works is you have a time where the clock strikes. So when that clock strikes, before that clock and after the clock, you have to have your signal steadily held at the input of the register. So the time before is called the setup time. That's setting up for the clock. And then there's a time after called hold time. Now, what you want, or what you don't want to happen, is for the clock to strike, you need to hold your signal at the front of the register for an extra 15 picoseconds, or whatever it is, in this case it's 20. What you don't want to happen is to have, say, a wire running directly like this. Because if you look, the delay in this wire is going to be really, really short. So if your wire feeds in a new value at 15 picoseconds, well, what's going to happen is we need this to hold for 20. The register is going to see, maybe the register accidentally reads like on the far edge over here, because this is kind of the range where the register can read in the value. If the register actually ends up reading here, and you changed the value here, then you didn't read in the correct data. So what happens is your circuit is going way too fast. There's a signal that propagates way too quickly through it, and it ruins the previous value before it has a chance to get read in. That's what hold time is. And so what we want is we want the hold time to be shorter than the minimum possible value. We need to make sure this 20 picoseconds is less than whatever the quickest path is through. If it's shorter, if this T-hold is shorter, then we're good. There's no way that this can somehow get in this range. If the other one is shorter, then we have a bad time. If it's 15 picoseconds, then we're not happy. We have to redesign our circuit. So that's why the inequality points this way. You want the hold time to be less.
Just follow my lead.
Sorry, I think you might have cut out a little bit.
Oh no, sorry. So we want it to be less than, right?
We want the hold time to be less than the minimum time through the circuit. That's right.
Okay. Sorry. I thought I was just looking at it and I saw that you had less than or equal to.
Well, you put the equal to because that's like the bare minimum, but in those circuits, you'd want it like that. You'd want it just less than because you need some leeway.
Okay, thank you.
Yeah, for sure. It's just, I write it the other way because that probably is the way you'd see it written out in a textbook, just to be consistent. But yeah, you're absolutely right. Generally speaking, just keep it as strict inequalities. Okay, so continuing from there, we have our setup for our clock time equation. Now, what are each of these terms going to be? Like, for example, PCQ. So I look at my clock to Q times. The maximum is 70. So this is going to be 70. Okay, what about the next one? Where's this term in my diagram? The TPD.
Propagation delay.
Delay on the combination logic.
Exactly. Both of you said the correct thing. So it's the propagation delay through this combinational logic, so the longest path, which we mentioned earlier was either A or B through three consecutive gates. Well, a gate delay goes from 55 to 100, and we're considering the longest time, so that'd be 100 times 3. That's going to be 300 picoseconds. And then finally, we have the setup time. This one, not really a trick question, it's just given to you, 60 picoseconds. So I won't ask you guys for that one. And so we have 70, 300, and 60. That's going to give us 430 picoseconds. However, that's not quite the final answer because they asked us for what? They asked us for the maximum operating frequency. That's exactly right. And so this is the clock cycle. That's how long, that's the period of your clock. So if I was to take a look at what the actual clock looks like, the distance from one rising edge to the next, all I'm saying is that's 430. picoseconds. What I want to know is the frequency of the clock. How many clocks I get per second. And so to get that, you just note that the period is inversely related to the frequency. And so you say the frequency of my clock is equal to 1 divided by the period of my clock, which is 1 over 430 pico, which I'm not going to calculate on the board, but is approximately 2 gigahertz. Do that in my head right?
Yeah.
Should be right. So around 2 gigahertz, a little bit faster. It should be like 2.3 or something. But that's how you would get your final answer. And so the boxed answer would be my frequency, my maximum frequency is about 200 gigahertz. Calculate the exact value for your homework, but I'm just putting that up on the board. So any questions for how I went from my clock to my frequency?
I just had a quick question.
Yeah, go for it.
So is this necessarily everything we need to do for the homework, or when it's asking for no clock skew, is that what we're doing when we're finding the frequency?
So when it says no clock skew, basically all that happens when you introduce clock skew is you change these equations. So this one and this one here, you add in a term to account for clock skew. When they say no clock skew, that just means that term isn't present in my equation. That's the only difference. The actual computations are almost identical, just with an extra term in there.
Okay, so you're just adding in the clock skew.
Yeah, it'd be like plus t skew here, or plus t skew here, or on the other sides, depending on the orientation of the skew, whether or not the clock for the input register, whether this one arrives first compared to that one, or whether or not this one arrives first to that one. That depends on, that'll affect which side of the equation you put your term on.
Okay.
Okay, any other questions? So with that in mind, that's the entirety of the first problem, part A of the first problem, which is the only part that they asked you to find. So any other questions for me?
Is that what clock skew as well?
It's pretty similar.
I feel like I understood the majority of number 1 pretty well. It was just the clock skew part that kind of like threw me off.
Yeah, because we like just went over that today.
Yeah, you don't have to introduce clock skew for these particular problems, you know, like front-facing way.
Okay, so then when it's saying for no clock skew, then it's literally just doing
what I did on
that.
the board. Yeah.
Okay, yeah, because that's what I was going to be doing when I was doing this. But then when I saw no clock skew, I was like, does that mean that we have to change out our circuit somehow?
Nope. It just means they're making it easier for you. Don't account for clock skew.
Got it. And just a quick question, like just for like pure like curiosity.
Yep.
When we do have clock skew, is it going to be also a given value,
Yes.
or
Yeah,
are we
that's
going to?
gonna be
Okay.
given to you. You can't
Okay.
really. I mean, you can calculate clock skew if you know like parameters about your wires and where the clock source is. But they're not going to talk about that. They're just going to tell you the skew is 55 picoseconds in that direction, which is to say this clock is slower. The clock arrives 55 picoseconds later for this one than this one. That's what they'll tell
Right.
you. So you don't have to calculate the skew.
Okay, gotcha.
Yep.
Next homework is part 2E,
Yeah, so including the skew.
and that's going to be skew.
Okay, yeah. So it's not too much worse than what we just did. You'll just have to remember, or you'll have to figure out the direction of the skew, it'll tell you, and figure out how that applies to your equations. Because if it's skewed one way, you put the term on one side. If it's skewed the other way, you put the term on the other side. And figuring that out is important. Remembering, you can just remember it if you want, but that can be kind of hard. So being able to figure it out on the spot is pretty important. But if you guys want, we can talk about that, or we can continue on with the next problem for today's homework, which I assume is what's asked.
Yeah, we can move on.
Okay. All right. So we'll talk about 3.34a. So that one, it's a similar problem to this. In fact, it's the same idea. It's just a different circuit. So instead of having 3 change XOR gates, we instead have 2 full adders that are changed together from one carry out to the next carry in. And so for this one, it's a very similar process. question for you guys. What would I do first? What would be my first step in analyzing this problem?
First, we want to take note of all of our given values, right?
Exactly, yeah. Step 0, basically, write down all the values that you're given because you're going to use those to plug into your equations. Step 0, part 2 is write down the equations you're using, right? So you have your TC equation, your clock time equation, and then you have your hold time constraint equation. So have those handy. And now, what's the next step? What's the step 1? What do I do with my circuit?
Figure out what your I figure out like the TC from D and TB, but mostly the TCD side.
Exactly, yeah. You're going to want to figure out what your critical paths are through your circuit. So recall that when I say critical paths, I mean either the quickest or the longest path. So the quickest is going to be your contamination delay through the combinational logic, and or just through the logic in general. And then your slowest is going to be your propagational delay. So that's what you are first tasked with doing. So we just look at the combinational logic in the middle and ask ourselves, well, what would be the slowest path? And if you guys had to guess, do you think it would be from the top 3 signals, so either C or the A zeros, or the A and B zero, or would it be from A1, B1? What do you guys think? If you had to guess for the maximum, the longest path.
Maybe C.
Pardon?
Maybe C.
Either C or A0, B0, so one of those. And I think it is. I think it's A and B for this one, but we'll talk about that. Why that is? That's dependent on the numbers you're given.
Okay.
So it's definitely one of those. And why did you say that it would probably be one of those?
Just noting the pattern that it goes through, seeing that it can go from C in to C out, and then to the other adder circuit, C in.
Exactly. Yep, that's exactly right. Because we're ending up passing through 2 different blocks of this full adder. Whereas if you went from A1, B1, you'd be passing through just 1 block of delay. So it's much more likely that going through 2 blocks of delay is going to be longer. In fact, it should be doubly as long as if we went through the other path. And so, yeah, let's talk about either A0, B0, which are the same delay input, or C, the C value. So in the problem, it actually tells us what the delay is for each of those. So the delay from carry in to carry out is 20 picoseconds, whereas the delay from A or B to carry out is 25. And that would be why A0 or B0 is the fastest compared to C, or the slowest compared to C. Okay, so keeping that in mind, we can now kind of draw out our propagational delay. So I'll go and draw it on the board. And I assume you guys are alright if I erase this? Okay.
It was just me.
Oh,
So I
really?
went for the homework with
Oh,
her.
this would be nice.
I was like, I don't get this.
I'm probably gonna go on Thursday.
It was really, really great. It was like I couldn't conceptualize or like what was happening.
Yeah. Yeah, I was trying to figure out the first one by myself. I was like, this is fucking difficult as hell.
Yeah. Well, the third problem also threw me. I was like, what's
Yeah.
going on?
Yeah, the circuit's kind of scary me a little bit.
All right, so I'm going to highlight my propagation delay through this circuit. So, like we mentioned, we're going to start at either A0 or B0. I'm just going to start from A here. And we said we want to pass through both of our adders. So I'm going to go down here to the carry out signal. So I'll label that carry out, which feeds into the carry in of this full adder. Okay, and so we say, well, what's that delay? What's the delay from A0 to C out 0? Well, we look at our instructions, and they tell us it should be, I believe, 25 picoseconds on the actual directions. So just that part, that's 25. And so now we're coming in through CN, and the only output that's registered is S1. You'll notice C out is an output, but it's actually not feeding into a register, so that's not an option for us. The only option here is S1. And so then we look at the delay from CN to sum. I can't remember what that is. I'd have to check. 20?
For propagation.
Let's see. I think I agree with you. CN to C out or to sum is 20 picoseconds. Yeah. Okay, cool. So this second wire here, that's an extra 20 picoseconds. And so what that means is that our propagation delay through all of this combination logic, or otherwise known as TPD, is going to be 45 picoseconds. Okay, so any questions about how we got there?
I guess I really don't know how the adders work at all. So
You don't have to. They're black boxes.
oh.
You don't have to know anything about the internals. All you need to know is what the propagation, what the timing delays are.
So how do we know that we're going from A0 down
Here.
there and then going to the next one?
Yeah, how do we know that's the slowest?
Yeah, how do we know that's the slowest? How do we
Yeah.
know that's the back to the
Let's consider, yeah. So let's consider options. So what I mentioned earlier is that it would probably be the slowest if we went through more blocks. So we need to somehow go from this block to that block, right? Okay, well the only path to do that is going from here downwards. So we have to start at one of these three. That was what I mentioned at the beginning when I asked which group. Do you think this group is going to have more delay or that one? And we answered this one up top because of that exact reason. So does it make sense that it would be one of these three paths? Okay, yeah, because we got to travel from here to from this adder to the next. Now we ask, well, this path or that path or that path? A and B are the same, so I could do either one of these. So now I just need to check which is worse, C or A0. In the homework assignment, it tells you that the delay from CN to C out is 20. And it tells you from A or B to C out is 25. Which of those is longer? So we pick A or B. So that's how I know to start here, go through there, and go out here. If instead I just started at A and went to sum, it actually details that as, let's see, 30 picoseconds. So from A to sum or from B to sum is 30. We got 45, but if we went, say, started here to sum, or A0 to this sum, or B0 to that sum, that would be just 30 picoseconds compared to this one we got, which is 45. So for your guys' problems, most of the time, it should be pretty obvious which route is the longest delay. Sometimes it's not, but most of the time, you'll just want to go through the most blocks, the most gates, the most blocks, whatever it is, for most of your problems. For actual work, if you were doing it for your own circuit, you typically wouldn't do it by hand. You'd actually let a computer synthesis tool generate those timings for you, because oftentimes when you create your own logic, like in an FPGA, there's lots of logic, and so your delays, your timings, they're going to be all over the place, and you just have so many different routes you can take through your circuit that you have no idea how you're going to do it. You'd have to go through every single combination. That's pretty tough to do. So typically we leave those timing calculations for longest and shortest delays to synthesis tools. But for these problems, it should be reasonable to either go through all the combinations or to intuitively guess as to what the longest path is. Okay. Now talking about intuition, what do you guys think the shortest path would be? If you had to guess.
A1, B1.
I forgot which group had the shortest delay. Was it
Well,
Is it A1?
well, it probably wouldn't be the same path, right? It'd probably be a different one. And so that means we're just going straight through to sum. So either the A's to sum or the carries to sum. Would you agree? Okay. Well, let's see. Which is slower, A to sum or carry to sum? And so then we look again at our list of timings.
C into sum is 15.
Yes, I believe that's right.
Maybe just
Contamination delay. Yeah. Yeah, contamination delay of C into either output. Yeah, okay. So it lists kind of midway through, or about 60% of the way through that paragraph, that the delay from C in to either output, either to C out or to sum, is 15 picoseconds. Whereas if you start at A or B and go to the output, it's 22, so that's longer. So the shortest path is going to be the carry. And so that's why C, from C in to sum, is our shortest path. And that, again, like the description of your problem said, is 15 picoseconds. And so that value is TCD. All right, I just want to mention something before I continue. This is unrelated to what we're doing. I heard some complaints from the grader about people who are still writing their code by hand. Don't do that. Type it up. It'll save everyone time, I promise. Don't write your code by hand. It's just tedious.
yeah. He sent a message after the first one.
Did he?
I think he was like, please type it.
Yeah.
Like to everybody.
Type your code. He said today to me that
Very
there's.
tedious to do even.
It is, yeah.
Yeah.
He told me today that there are still people doing that. So I just want to again say, if you know any of your friends who are writing out their code, please tell them to not. Okay. So any questions for what we've currently done? I realize that I'm blocking most of it, but like the process that we went through. Any questions for anyone? Okay. So we went ahead and got the propagation and contamination delays. So the propagation delay through the logic was 45 picoseconds, and the contamination delay through the logic was 15 picoseconds. And so now we can again just look at our equations that we have for timing analysis. So the first equation we're going to do, again, is the hold time, because if that doesn't work, the clock time isn't going to work at all. So we check the hold time first. So again, we want the hold time to be shorter than any possible signal coming through, because if it's longer, if it interrupts that hold time phase of the register reading stuff in, it's going to interrupt the read in, and it's going to be wrong. So we have the time to come out of the register, the shortest time to come out of the register, plus the shortest time delay through the combinational logic. And that has to be greater than the hold time, or in other words, the hold time has to be less than that. So what is the hold time in our circuit for our registers? Yeah, it looks like it said 10 picoseconds. And before I even plug in TCCQ, TCD is what? Yeah, we said earlier that that's 15.
We're already there.
So we're already there. What this means to me is that it doesn't matter what your register's inbuilt contamination clock to Q is for this circuit, we're already good. But just for the sake of fully proving the point, TCCQ should be given to you as well. And I believe, let me check. Contamination clock to Q of 21, that's right. Again, all these numbers just come from the problem instructions. And so you add those up, and you get 36 picoseconds. And so 10 picoseconds is definitely less than 36. And so you're good. Your hold time constraint is met, and we can move on to the important calculation of figuring out what our cycle time is, and then the frequency. All right. Let's check your guys' memory. I don't have it on the board. What is this equation here? What are the components, the three pieces?
T setup and
TPCQ.
Yeah, T setup, and then what'd you say in Discord?
TPCQ.
Yep, exactly, TPCQ. So we have reading out of the register. That's the first stage, so I'll write that first. And then we have going through the logic, that's TPD. Going through the combinational logic, sorry. And then finally, waiting at the front of the register. That's T setup. Okay, and so now we just take these and add them up. Well, TPCQ, that should be given to us, I believe, is 35. Clock to Q propagation delay, yeah, 35. Okay, and then we look at TPD. That was the number we calculated earlier as 45 picoseconds at the beginning of our analysis. And then T setup, which again is just a given value that should just be in the description of your problem. So I'll take, 30 picoseconds. And so now we just have to add these all up. So I get 35, 45, that's 80. 80 plus 30, that's 110. Okay, now I'm going to box this. However, like I mentioned, this isn't our final answer because they didn't ask for the clock time, they asked for the
Frequency.
yes, the maximum operation frequency, exactly. And so how do we get the frequency from this, from the clock time?
Take the inverse.
Frequencies.
Yes,
to
the reciprocal
1
of
over,
the inverse, exactly.
Yeah.
So we do 1 over 110 picoseconds. We run that calculation. We should get about 9 gigahertz when we run that through. And so running that calculation, we get about 9 gigahertz, and that would be our final answer. Any questions on that?
Just a quick question.
Yep, go for it.
So since it doesn't say that we need to turn it to like gigahertz, unless it's like implicit that we need to turn it into gigahertz, can we just set it as 1 over 110 without having picoseconds so that unless we have to convert it?
So here's what I'll tell you. If someone were to walk up to you and say, hey man, my circuit has a frequency of 1 over 110 picoseconds, what would you say?
I don't know.
I'd be like, okay, cool,
Yeah.
good for you. Now, if they came up and tell you my circuit runs at 9 gigahertz, you can literally think, giga means billion, that it runs at 9 billion cycles a second. So, yes, calculate it and write it down.
Okay,
I don't think she'll accept it. She'll probably give you some credit on tests if you just put 1 over 110, but she'll probably mark you off and say, just change it to frequency. And then I would also recommend making the conversion to giga instead of leaving it in hertz, because you could put 9 billion hertz if you want. It's just a lot of digits, and treat it like your circuit's your EE220 class, just like when you do if you're taking it with Baker, turn stuff into kilo ohms or into mega ohms, things like that. So just keep the engineering units in your answers. That's typically what you want.
Okay, thank you.
Yeah, for sure. Okay, any other questions? Okay. So the last question, I believe, was not in the book. It was given to you, right? Okay. And then what was
Yes.
that question?
The light traffic.
Oh, that's right. It's the FSM with the 3 gates leading into it. Okay, cool. And they just want you to, again, well, it's the same problem. Same exact thing. It just looks a little different, right? Because in all these problems I've drawn 1 register at the beginning and 1 register at the end. And I say, I read out of this 1 register through logic and then read into another. Here, though, you're reading out and into the same register. If it confuses you to have it drawn like that, you can draw it separately. You can have, say, 2 registers just for like the diagram to help make sense to you. But it doesn't matter. You can still start the output of 1 register, feed through some logic, and back to the input of that same register, and it works exactly the same. There are no differences computation-wise. Okay, so for that logic, again, we're given a bunch of default values for like hold time, setup time, delay through gates, and all that stuff. So here's what I want you guys to do. If you haven't already worked on it, work it through for maybe a few minutes. I'm going to erase the stuff on the board, so if you want to take a picture, you can. And just either continue working on it or check your work.
Nitty, stop.
What's that?
Sorry, my dog was barking after I was muted.
Oh, no, you're good. Don't worry about it. It's fine. I mean, it doesn't really make too huge of a difference. Okay, cool. So I've written it down. Now, just as a preemptive thing, these values, S0 and S1, are registered values. They come from a register, whereas TA and TB, maybe they're registered. No idea. Could be some external input from just an asynchronous source. Maybe it's not registered. So what I'll assume is that since S0 and S1 participate in the same gate delays as TA and TB, that these guys take longer to go, longer to propagate. And the reason why is because they have to first be read out of a register, whereas these, maybe they don't have to be read out of a register. But for sure, these do. So I'm going to take these to use as my longest delays. Okay, so keeping that in mind, we have a 3-input gate delay going into a 2-input gate. And then here we have another 3-input gate delay going into a 2-input gate. And then on here we just have a 2-input gate. So where do you guys think would be the longest delay, and why? Would it be like a path going through here, through there, through there? Which one?
The one that has the input for TA.
This one?
Yeah.
Yeah, I think either one of these is fine. You're given the delay for a 3-input gate, and you're not told that these inverters have a delay. So I'm just going to be assuming for the sake of this problem that that is included in the total gate delay. Sound good to you guys? So these two are basically like the same delay, and they both end up going through the same OR gate. So actually, it doesn't matter which path you take. They're both essentially identical. So it doesn't matter which one of these you do. You just pick one of them and say, well, let's talk about our delay. We have to get read out of a register, go through a 3-gate, and then go through a 2-gate. And that's our total TPD. So I'll write that down. So for TPD, we have a 3-input gate delay, which is how long?
Is 50 picosecond.
Okay. And then we have a 2-input gate delay.
That is 40 picosecond.
Just so you guys know, not necessarily all gate delays, even if they're both 2 inputs, are going to be the same. You could have a different one for an AND gate versus an OR gate versus an XOR. So just keep that in mind. You can have different gate delays, and you might be given it in a table. And that's when it becomes more complicated to figure out what the delay is through your circuit. If you have many different types of gates and many different routes over those gates, it's really hard. That's why you leave it to synthesis tools. Okay, now what about TCD, the fastest time?
It's just S1, S2 through the 2 input gate. But then
Yeah.
you threw me when you said it's coming from a register, so it has more, like maybe
More delay.
TCQ.
Well, yeah, that depends. So maybe these have no delay. Say, just as an example, say these don't have any. This path through TA through TB goes through a 3-input and then a 2-input. The path from S0 or S1 reads out of a register and then through a 2-input. So the thing we'd have to check is see which one is faster. Is reading out of a register faster or going through a 3-input gate delay faster? So which is it? 3-input gate delay, the contamination delay of a 3-input gate is what in this problem?
Is it what?
What's the contamination delay through a 3-input gate in this problem? What do they tell you?
The 3-input gate contamination delay is 20.
So 20 picoseconds versus, and then what's the contamination clock to Q?
The contamination clock to Q is 15.
15. So which one's faster? 15. So no matter what, even if these happen to be registered values, those are going to be faster regardless. So in this circuit, it didn't matter.
It didn't matter. Okay. Yeah, that part, like, I didn't even think about it. But they also, those two fed into the 3-input gate as well. So, like, when it being recognized, because it would have to factor into.
Well, because this one is a different route, because they have completely different routes, right?
Oh, yeah, no, yeah, I understand.
Yep. Okay. So now the next thing is we have read out of our register, and then we
Wait,
go
wait,
through.
wait, wait, wait. Sorry. The TCD of a 2-input gate is actually 10 picoseconds.
Yeah, but this one was, well, I guess I shouldn't write this. Sorry, I should write that.
TC. Oh yeah, that one is 15.
Okay, well, let's just consider, so that's overall delay. Let's just consider what the fastest path is. Yeah, let's ask what is the fastest path again. So remember this delay is 15 picoseconds to get read out of the register. And then into this 2-input gate delay, that was 10 picoseconds. So that's a total of 25. So it's pretty fast, starting from here. And then again, if we were to look at TA or TB, we go in through a 3-input, and that one was how much?
3-input TCD was 20.
20 plus was 2, which was 10, right? Yeah. So again, either way we look at it, they're pretty close, but this is definitely the fastest route. All right. So TCD, that's the delay for this guy to go through that XOR gate, that's 10. And then TCCQ, that's 15 picoseconds. What about TPCQ?
TPCQ was 25 picoseconds.
Okay, almost done asking you guys questions. So we now have to find the hold time and the setup time, which should be given to us again. So what are those?
Setup is 30. Hold is 17.
Said 17?
17. Yes.
Okay, so now we can go ahead and write our equations. So which equation should I start with? What do you guys think? What equation should I do first? The hold time or the clock time? Sorry, the hold time or the setup?
The whole time.
Hold time, yeah, because if that doesn't work, then nothing else is gonna. So again, we want this hold time to be smaller than the fastest path through the entire circuit, and that fastest path consists of the time to get read out of your register, so TCCQ, plus, and then the time to propagate through the logic, which is TCD. And so we have the T hold is 17 picoseconds. And that has to be less than or equal to TCCQ. We said that was 15 at the top. So unless there's a straight wire from here to there, then we're probably good. Let's see. TCD we calculated earlier to be 10. That's still pretty short, but we satisfy our equation. This is going to be 25. So we have 17 picoseconds less than 25. That is correct. So that means our hold time constraint is met. All right, so now that our hold time
Just
constraint is
follow my
met,
lead.
all right, so now that my hold time constraint is met, what do I do next? Yeah, we do the setup time equation, or the clock time equation. So we have so what's the equation for clock time?
TPCQ plus TPD plus T7.
Okay, and what's TP's and Q? Looks like it's 25. We'll totally right up here. And what do we get for TPD?
90.
Yep, we calculated that as 90 earlier. And then we have the setup time, which we have up here as 30 picoseconds. And so the last step, the hardest one, adding numbers. So we have 90 and 30 make 120, and then plus 25 should be 145. So the smallest clock period is 145 picoseconds, which is to say that the maximum operating frequency is equal to 1 over that, 145. And then that value will be somewhere in the range of 6 gigahertz. And that's the entire problem. Hooray! We did it! We've done it! The homework is finished. Now we can wait until Wednesday office hours and then go over and then do it a few hours before. Yes, start that day. Yeah, started at 9 p.m. on Wednesday. Okay, so you guys have any questions regarding that process or anything we've gone over, or conceptual questions, or really anything? Got about 8 minutes left. Okay, well, like I said, if you have any questions, just ask me. Yep.
Oh, sorry. I was just wondering, if there's a maximum frequency, is there a minimum frequency?
Great question, yeah. So if this is my maximum frequency, the 6 gigahertz number, you can run it slower than that, as slow as you want. You could run it at 1 hertz. It doesn't matter. So there isn't really a minimum frequency. It's just however low you can go without getting your customers angry at you for having a slow computer. So that's your minimum.
I used to work at Geek Squad and I used to build custom computers.
Really?
Would have to overclock
Because it's too slow at base.
them. Or I just tell them to buy a new computer.
Yeah. But yeah, no minimum operating frequency. Slow as you want. Though I will say that this maximum operating frequency, it's true for this circuit in isolation, but you have to consider that this probably isn't the only thing you're going to have in your entire design. You have multiple circuits running at all that have to be run at the same frequency, probably. Not necessarily all the time, but probably at similar frequencies. And because of that, you have to make sure that the maximum time, or the maximum frequency works for all of them. If you have another circuit just like this, except more delay, you have to drop down your frequency because you need to account for both cases. What else? Running at a higher frequency burns more power when you have it in a circuit because the power is consumed when you flick the clock source on and off. What happens is the transistors either activate or deactivate and change state. That act of changing the state of the transistor burns power. And so typically what you'll see in low power operation devices like microcontrollers is they have what's called clock gating. So if you have a component in your microcontroller that you aren't going to use for your particular application, you have not the clock fed directly into the registers, but you have it feeding into an AND gate and then into a clock. If you set the other input of that AND gate to 0, the clock is never supplied. If you set the AND gate at 1, the clock is supplied. And so what that means is that you're not going to burn useless energy, or you're not going to burn energy on a useless operation that you're not even using for your application. So that's an interesting thing to note. Higher clock speeds, you're burning power more quickly. That's about it for trivia, I guess. Any other questions for me?
I mean, I'm going to the homework.
Go for it.
Friday. For the FPGA, like, I guess if I want to focus the project, lasers and stuff like that. Should I focus on, like, I guess connecting the sensors and stuff like that? Maybe how you utilize the FPGA?
Thank you so much.
Yeah, I mean, sensors is a good way to do your project. So, you have a sensor to measure the water in a bottle. You have a sensor to measure the light, the luminosity in the room, or whatever it is. And you use that sensor, you read it into the FPGA, you do something with that value from the sensor, and then output something with it.
Yeah, because from the list that you told me, a lot of them, I guess, are not really focused too much on using them. So,
Yeah.
I'm trying to
Like,
figure
those
out-
are interesting projects that you gave me, but
Yeah, I'm just trying to figure out how like utilizing the FPGA.
definitely.
So I was like, maybe I could try to utilize these kind of sensors. What if I had like motors, maybe? And
Yeah, you can totally have it controlling motors.
to encode them to
That works.
certain stuff.
Yeah, you can totally do that. Though I will say controlling motors is a lot easier if you're using a microcontroller. But you could totally do that on an FPGA, yeah.
Maybe I could build my own also laser detector. But that would also guess I'll have to get some motors and then encode them somehow, and then.
Yeah, I mean, it depends on the motor you get. Some you can just send a PWM. A PWM is just a pulse that you can change on the fly.
Right.
So it's called PWM, stands for pulse width modulation, and it's just a pulse wave. And you send it at a higher frequency if you want it to run faster, and you send it at a lower frequency if you want it to run slower, that kind of thing. And you could on your FPGA make a PWM generator, and then have some external inputs like switches on your FPGA control what the pulse width generator is going to do, what the frequency is going to be, and then you'll see that output on the actual physical motors as they rotate faster or slower. That's an example, yeah.
Another option I was thinking maybe if I was, I guess, rotating mirrors in a certain axis, that could, like at a certain angle, they could pass by a kind of a light sensor, so kind of give like a reference point to stay at. I don't know.
Yeah, you'd then have to have a light sensor to figure out what the best mirror angle is, and then you'd have to account for a lot of things, like if your motors have high enough torque to actually spin those big mirrors that you're going to be putting on them. You can't use tiny little baby motors that they have in the supply room. You might have to buy your own, or get a big motor from them. And then you'd have to figure out the protocol for that motor, how it works, what kind of pulse widths work for it, or if it even works on PWMs. A whole bunch of considerations.
Yeah.
No, it is always going to be a lot. When you dive into it, that's when the fun begins.
Well, at least like trying to figure out. At least I guess.
It's good that you're starting on early, or thinking about it early.
I guess I'll get something simple by the end.
Yep. All right. You have a good one. Okay. Any questions for me? On the Discord, any questions?
Oh no, I'm good. Thank you.
Yeah, for sure. All right.
Have a great night.
You too. See ya.
Thank you. Bye bye.
And I'll stop.